Alright, hi guys, and welcome to another video on the channel. This one is covering sound, another chapter which is important with regards to your unit 3 on waves. So this is what we are going to have a look at now. So again, we are using the same handouts. So first blank, this is a dash wave produced by vibrating sources. So the idea is that this is a longitudinal wave. And what longitudinal means, you probably remember from the discussion on general wave properties, which is that the direction of vibration and the direction of wave motion are parallel, right? For transverse waves, they're perpendicular. So these are made of compressions and rarefactions. So pretty much like how we used to talk about transverse waves in terms of troughs and crests. So here we're talking about compressions and rarefactions. So at compressions, air particles are the closest. This is why it's called a compression. And this leads to the highest air pressure. So this is something you're supposed to know, and we'll also see this in the context of the diagram below. Similarly, at rarefactions, air particles are the furthest apart, and this leads to the lowest possible air pressure. So if you look at this diagram then, so there's this loudspeaker at the left, and this is creating, basically this is transmitting sound. So again, I know that in this case, the wave is in this direction. So this is the direction of wave motion. And what's going to happen, because this is longitudinal, is that the particles will also vibrate back and forth along the same direction. This is a very popular question which is asked a lot in paper 2. So as we can see here, regions like these would be called compressions, because this is where the air particles are closest together, and where they're the furthest apart, something like this, would be called rarefactions. All right, not rare fractions, it's rarefactions. So again, another popular question in terms of the context of past papers is that how does the vibration of the loudspeaker cone basically produce, how does it cause sound to be transferred? So the idea is that as the cone moves forward, and it does, and we'll talk about this in the context of electromagnetism later. So the idea is that as the cone moves forward, it also pushes the air particles closer together, and this creates a compression. But again, it keeps on moving back and forth. So basically there's some idea related to electromagnetism here. So force is applied, which is sometimes forward, sometimes backward, in terms of the signal which is being supplied here. So whatever sound, for example, you want to play. And then as the cone moves back, the air particles move further apart, and this creates a rarefaction. And this keeps on happening, and this is basically creating the compressions and rarefactions, and this is how sound travels from point A to point B. So sound requires a medium. It cannot travel through a vacuum. This is, by the way, true for all longitudinal waves. For transverse waves, the exception is the EM spec, which has been covered in another video. So those don't require a medium, but apart from that, all other waves do require a medium. So there's an experiment to verify this. It's called the bell jar experiment as well. And the idea is this. So you will have a glass bell jar. It's going to be secured using this cork. And inside this is placed an electric bell. Additionally, there are also some connections to a vacuum pump here. So what's going to happen here is this, that initially you can hear the sound. Basically from the ringing bell as the gong keeps on striking. This is exactly like your school bells. So you'll see this hitting the actual bell. This is called the gong. So that's hitting the bell, and you'll also be hearing the sound. But then you'll switch on the vacuum pump, and what's this going to do is it's going to be removing air from the glass jar. So as it keeps removing air, the sound keeps getting fainter and fainter, so the volume starts to decrease. And when a full vacuum is established, what you will see is that the gong will keep hitting the bell, but you will not be hearing any more sound, because there are no more particles. And as we just talked about this in the context of compressions and rarefactions, you need particles, because that's how sound will travel from point A to point B. So the idea is also this, that sound travels fastest where air particles are the closest together, because if the air particles are the closest together, then those movement, the back and forth movement, is going to be transmitted the best. In a way, it's also really similar to the idea of transfer of thermal energy and the idea of conduction in particular, where we said that conduction would be the best in solids because the air particles are closest together. Similarly, sound would travel the fastest in solids because that's where the molecular spacing is the least. So speed of sound in solids would be the greatest, and the speed of sound in liquids would be second best, and speed of sound in gases is the worst. So that's the slowest. So we also are expected to know uh, this value for the speed of sound in air. Our syllabus says we can say this to be anywhere between 330 and 30 or more, and there's no wrong or right to this. But just be warned that if the examiner does not give you a value for a calculation maybe, then you'll need to use a value between the 330 and 350 range. Speed of sound in liquids, you expected to know approximate figures. So this is approximately 1500 meters per second. This is approximately 5000 meters per second. Again, these are just ballpark figures because in reality it would depend on the actual type of material, something like the temperature. All of these would impact how fast sound travels. On the other hand, when we talk about light, and this we've already talked about, so we know that speed of light in gases or in a vacuum is the fastest, it slows down in liquids, and it slows down even more in solids. So this is an important comparison that you must have in your mind. A lot of students do tend to get confused with this. And the reason why this is so is basically because one is transverse and the other is longitudinal, right? So that's what you need to remember here. Measuring the speed of sound, experiment number 1. So student 1, he fires a starting pistol that you've seen, for example, in races. And when student 2 sees the smoke from that pistol, he starts a stopwatch. Now, obviously, when we look at somebody who's maybe next to us and he's firing a starting pistol, both things seem to be instantaneous. But when done through a very large distance, this will become not as simultaneous. So you will see a difference there. So whenever he first sees the flash, that's when he starts a stopwatch, and when he sees the smoke, that's when he stops it, right? Sorry, I might have said it the wrong way around. When he sees the smoke, that's when he starts the stopwatch, student 2 we're talking about. And when he hears the sound, that's when he stops the stopwatch. All right. And why can this be done? Why do I see the smoke first and why do I hear the sound later? That's because light is much faster than sound. For example, when it's raining and when lightning strikes, then you see it first and then you hear the sound. Again, that's also a consequence of this. This is a common question which is asked in MCQs, which is how much faster is light as compared to sound. So we know that the speed of light is 3.0 into 10 to the 8 meters per second. Speed of sound is 330 to 350. Just to make the calculation really easy, we can just right now estimate this as 300. So I would say this is 3.0 into 10 to the 2 in a standard form. So 3's cancel out. Base is the same, they're being divided, power subtract. So the answer here is 10 to the 6 approximately. And what this means is that light is 1,000,000 times faster than sound. All right, so that's the idea here. So the distance between the students and the measured time, the time which is measured by student 2, it can be used to calculate the speed. And again, as far as experiment goes, this is one where we can do multiple readings. So by taking multiple readings for the time and then averaging, this would reduce uncertainty in time measurement, because we know that there's human reaction involved here, as the student 2, he is controlling the stopwatch himself. So for example, if we have to find the average time here, and this is what a possible ATP question could look like, maybe you go through the past papers and find one exactly like this. So there are three readings, adding all of them, dividing by 3 gives us the average value for this. So let's go ahead and do this on the calculator. Divide by 3. So this turns out to be 4.55333333. This is a recurring number, so 4.55. If something like this ever comes up in your ATP, remember that it should have the same precision as your original values. So because these were 2 dp, I also wrote this as 2 dp. And then for the speed, I can just use the distance over time formula more appropriately, change in distance over change in time. So distance is 1500 meters as given here. Time is 4.55 seconds. It would be better to use the calculator value. So this turns out to be 329, which is approximately to 2SF, the same thing as 330 meters per second, right? So this is how a possible experiment could look like. What are the different improvements we could suggest to this experiment? Now, this is what we'll be discussing. So using a CRO for time measurement rather than having a person use the stopwatch, that could be better. And with the CRO, we'll be discussing this later in the electromagnetism unit as well. The idea is that you'll have the sent out pulse, you will have the pulse which is detected, and if you have these on the CRO and you have these plotted on the display, then what would be given to you on that scale on how the CRO works is the distance between the two. Well, this distance is not the actual distance between the students, for example, if you may think that it's that. It's just that whenever you use a CRO, you have a certain setting on it, which is called the time base. So the time base setting is usually given in some units of seconds per division or per centimeter. So for example, if this is 5 meters, if this the time between, if this is the distance between the two, the formula is something like this, is that if you multiply total distance is zero point 0.9 centimeters, then just doing this cancels both of these out, and this turns out to be 4.5 millisecond, right? So then you can also use something like this in the calculations back again, and this is just much more appropriate. This creates a lesser uncertainty. Other improvements, so you could use an open space, so using open spaces. And what's the advantage of using open spaces is that it avoids echoes. But again, that's again with this experiment, you'll always have some uncertainty because you'll also have the spreading of sound. That's always going to happen. Something that you can do, and it's really not a change to the experiment, you can use a bit of common sense, and you know that the human reaction time is always a fixed magnitude. But if you use a larger, if you get a larger time, it would be a smaller percentage, a smaller fraction of that amplitude. So what you could also suggest is that you can, okay, so let me get rid of spreading of sound because that's not really a improvement. So what you can say is that by using larger distances, you'll also get bigger time values, which is going to reduce uncertainty due to the human reaction time. So next up, reflection of sound. This is also known as echoes in this chapter. So the idea is that again, if you have a loudspeaker, you're sending sound, and to avoid spreading, you're using these maybe like these cardboard cutout cylinders. And this is basically striking a surface, and from that it's being reflected. And this is inspiration from a past paper that I've taken for this year. And you can change the angle of the cylinder that you basically have applied to either an ear or a microphone. And where would you hear the loudest sound? So again, the idea is pretty much the same as we used to talk about this with respect to light, which is that for the sound to be the loudest, this means that this angle, which is the angle of incidence with the normal, and the angle of reflection, they should be approximately the equal. They should approximately be equal. So if you place your cylinder like this, and if this is where you position your ear, that's where you would hear, where you would expect to hear the loudest sound. So the cardboard tube is again used to prevent spreading. Loudest sound is observed when the angle of incidence is equal to the angle of reflection. Now, as we studied with reflection back in waves and also with light, speed, frequency, and wavelength do not change, but in reality, the amplitude of the wave may change slightly because of some loss of power. This we studied back when we were studying general wave properties, that amplitude is a direct indicator of the power or the energy content of a wave. So echoes can also be used to measure the speed of sound in air. So let's say this guy, if he was actually using a pistol, he did the experiment irresponsibly. Student 2 is now dead. Apologies and condolences to his family. So he's no more. Now he has to do the entire experiment on his own. So this is the sound which would be sent out by the first shot. And if he's standing in front of a wall, this is going to get reflected. Now what he is going to do, and he's obviously going to face difficulty, because not only does he have to carry the burden of murdering his friend in his heart, but he also has to do everything on his own. He has the gun in one hand, he has the stopwatch in another hand, and a very heavy conscience. So what's going to happen now is this, that whenever he basically fires the gun, that's when he starts the stopwatch, and when he hears the echo, that's when he stops the stopwatch. Now if we think about it, and the time that the student would get from measurements is really the time it takes for the wave to go, strike the wall, and then come back. So this is the time that we would get from the stopwatch. Now if I think about it, in that time this sound traveled this distance once on the way to the wall and another time on the way back. So the revised formula according to echoes for the speed of sound would be 2d over t. Again, as with the previous case, I could suggest the same improvements. So CRO can again also be used to improve time measurement here. Again, something else, and this is just stuff you need to know, not a lot of thinking really involved with the chapter of sound, is the audible frequency range. So you need to know that this is from 20 hertz to 20,000 hertz, and 20,000 hertz is sometimes also written as 20 kilohertz. So sound which is less than 20 hertz is called infrasound, and similarly sound which is greater than 20,000 hertz is called ultrasound. And ultrasound is pretty cool in terms of its applications, and that's what we'll be talking about next. So there are a few uses of ultrasound in our syllabus that we need to be aware of. So the first one of these is called sonar methods, which is basically using ultrasound to obtain some information. So ultrasound probe sends out waves which are then reflected by a barrier. And again, something which is also cool about ultrasound is that the probe in itself is also the emitter, it's also the receiver. So the same probe also receives the waves. And the emitted and reflected waves can then be analyzed on a CRO to obtain different information. Now, what I'm about to tell you is not really part of the syllabus. This is just general information. For example, if some of you are into watches and stuff, then you know that a lot of watches run on what's called a quartz crystal, right? Similarly, there's also something else called a piezoelectric crystal, and that's how we actually get ultrasound. So the idea is basically this, that with the crystal, if you apply a voltage, some electricity to it, it gives you the wave. And similarly, if that same wave is incident on it, it produces an electrical signal back again. So that's why it's the same thing, which is the emitter also, and it's the receiver as well. Now, the idea here is this, that the emitted waves would go, they would strike some surface and bounce back again. This is how we obtain different information through the use of sonar methods. So the question, for example, in this case says, find the depth of the seabed given the emitted ultrasound pulse takes 2.8 seconds to be received again. So if it takes 2.8 seconds from it to go and then to come back, so this is basically echoing. I can use that formula, V equals to 2D over T. Again, it's given speed of sound, and you might be saying, well, we're doing ultrasound. So the only difference between ultrasound and sound is in terms of frequency, and then obviously in terms of wavelength, the speed is constant. So 1500 meters per second, the speed of sound, is naturally also the speed of ultrasound. So 1500 equals to twice the distance, the depth that we're trying to find out, divided by time. And from this we get D as 2100 meters. Now, some of you might have also realized this, and this is exactly the thinking I want to inculcate in you guys, that if it takes 2.8 seconds from it to go from here to here and then come back, then I can also say that, all right, one way it then takes just half of that. It takes 1.4 seconds. So you could have also done it using that, but in that case you would not use 2D, right? Because that's just one of those depths, one of those distances you're traversing. So the time it takes for the wave to be received, this tells us the distance from the boundary, because naturally the further away the seabed would be in the example above, the greater the time would also be for us to get the sent wave back again. Also, for example, in this case, maybe the seabed reflects a lot. If you have a fish here, maybe the fish absorbs a lot and reflects very little back. So if it reflects very little back, this means that the amplitude, because of the energy being less, some energy has been absorbed. So by the energy being less, the amplitude of the reflected pulse would also be less. So this basically tells us the nature of the boundary. So what is this boundary made of, right? In one case, it's made of the seabed. In the other case, it's just made of fish skin, so fish flesh, right? Application number 2 is called jewelry cleaning. So with jewelry cleaning, you have a sort of an appliance, and in that appliance, what happens is you place your object to be cleaned. It could be glasses, could be jewelry, and that's immersed in some solvent. So what happens is that when the appliance is turned on, waves are created, these strike the object, and for the objects you have some dirt particles which are basically stuck in place. Those are then dislodged by the wave, and the solvent dissolves and carries those away. So that's how cleaning is achieved. Similarly, medical imaging. So for medical imaging, we also did this in X-rays. It's also used in ultrasound. So for medical imaging, what you need to know is that ultrasound pulses are sent into the part of the body that needs to be scanned, pretty much the same as X-rays. But the difference is this, that because we are analyzing the ultrasound, and the ultrasound probe is also the emitter and the receiver, so it's really the reflected ultrasound that we get back from, for example, the fetus inside a stomach. That's what is used to produce an image. This is different for X-rays, because for X-rays, the X-ray that actually gets through the bone that's what produces that blackening on the screen, and that's how we get an image, right? In this case, it's the reflected ultrasound which produces the image of the fetus. Again, some general knowledge. In ultrasounds, you might have seen that, for example, for pregnant women, there is this gel which is applied on the stomach, and this is always done. The reason for this is ultrasound, if I were to have this incident normally on somebody, it would just reflect off them. So the gel, what it does is it improves transmission into the stomach, because that's where we want the ultrasound to go, and then it gets reflected from the fetus chilling inside the stomach. All right. So since ultrasound is not ionizing, this is basically why it is used for fetal scanning. And basically, unlike X-rays, it does not carry the dangers that carries of cell mutation, and obviously we don't want a fetus who is already in a very precarious stage of life to basically be hit with X-rays, because that has an ionizing effect and it can cause different hazards as well. All right, properties of sound. With properties of sound, the first one, this is actually wrong. It should have been amplitude. No. This is loudness, my bad. The next one is wrong. So the loudness of sound, this is determined by the amplitude. Again, pretty basic information you just need to know. So the greater the amplitude, the louder the sound would be. For example, in this case, you can see that this one has a greater amplitude. Again, both of these are displacement time graphs. So I would say that blue is louder. Next, this one is wrong. Instead of frequency, this should have been pitch. But again, you guys probably got it now. So the pitch of the sound is determined by frequency. And by determined by, I'm basically talking about a direct relationship in both of these cases. And again, if this is not clear, by direct, I mean that if one thing increases, another thing also increases. So the greater the amplitude, the louder the sound. The greater the frequency, the higher the pitch of the sound. So in this case, if you see, both of these have the same amplitude, but this one is higher frequency, because in the time that for red, I have only one wave, for blue, I have two waves, right? So blue is the one which has a greater frequency. So I would say this is higher pitched. All right, this one was louder in that case. The third property, which is called the quality or the timbre of sound, is basically has to do with this idea that the higher quality sound is purer and has less frequencies, which is basically apparent as noisier. All right. So in this case, if I look at the diagram, so this one is the purest possible sound, because this has just one frequency, right? Just one frequency of this major wave. But if we talk about the other ones, you have a few of the frequencies, smaller frequencies being added on here. So we'd say this one, the number one, this is the purest sound, because this has no noise. And also I would encourage you guys to actually listen to what one frequency of sound basically sounds like, because that's just like one monotone voice all throughout. So you'll just hear like a beep all the way through. But for this one, and this is what actually human voice sounds like, hence the waveforms that WhatsApp shows you. So basically, you know that we have a lot of variations here. So this has more frequencies added on here. So this is impure because of these frequencies which are adding on noise, and this is the least pure because as you can see this has a lot of noise added all throughout the wave, right? So amplitudes are the same, the frequencies are also the same, the major frequencies, but then you have these smaller jagged zigzag lines added, which is basically worsening the quality of sound. So that's basically all that you need to know about the chapter of sound in O levels and IGCSE physics. So I hope you guys learned something in this video. Like, share, and subscribe with your friends, with a student who might need to revise this topic. Also, let me know down in the comments if you have any video suggestions or any more content videos that you would like to see. I'll be happy to hear from you and see you in the next video. Bye.